Hello everyone, welcome back to another round of AI Eng show. We have with me wonderful guests today, Michael and Manoj from Uber. Michael and Manoj, welcome to the podcast.
Thanks for having us, Parth.
Yeah. Before we go into our topic today, Michael and Manoj, do you guys want to give a quick intro?
Sure, Michael, go ahead and then I can go.
Okay, sure. Michael, I'm working for Uber Seattle office, and most specifically on the airport team. Yeah, I have been Uber Seattle office for more than 6 years. Now I just being like senior staff engineer. I'm being the Uber tech lead for the whole airport and travel space here. Yeah, go ahead.
Thanks, Michael. Hey guys, my name is Manoj. I'm a product manager based out of Seattle. I actually used to be on the same team as Michael, so we both used to work on airports. I've since moved from the last year to the AI team, so both products are very close to my heart.
Yeah.
Lovely to have both of you. And we are talking today about this blog that these guys have written, forecasting models to improve driver availability at airports. And I know specifically traveling, I was just telling Michael that I've traveled recently to Dubai, India, and everywhere I've had like different flavors of experience with Uber in terms of airport experience. So this is like a problem that is very close to my heart. So I would love to like learn more what you guys did from the blog perspective, and maybe we can start with the problem space. Like what kind of triggered you to kind of think about improving the airport experience, right? Because it's a unique challenge for sure in every airport. So Manoj, maybe you can start here.
Yeah. So before I get completely into like why we did it, let me tell you a little bit more about like airports themselves and how they're different than traditional Uber. So when you think about like Uber matching and how riders and drivers get matched, generally what happens is a rider makes a request and then a driver gets matched based on their ETA to the rider. But there's a difference at airports where generally we have staging lots and we have contracts with these airports. And so all the drivers are kind of in the same place. And so pretty much what happens then is a driver has to decide, hey, do I go to this airport? Do I go to the staging lot and wait for a certain amount of time before I get an offer? Or is it better for me to like drive in the city? So it's actually like a conscious decision they have to make on should I go to the airport? It's not as easy as them being like, oh, I'll stay in my home or I'll drive around and I'll get an airport offer. The nice thing about the airport offers is that generally they're higher than city offers because people are willing to pay more to get out of the airport and go home. And so when Michael and I and like the team built this, essentially one of the main issues was we just got out of COVID. And so during COVID, there was like no travel. But travel had started to recover. So a lot of consumers were traveling, but we noticed that we didn't have a lot of airport supply at the airport, meaning that there weren't a lot of drivers coming to the airport. And so then what we decided to do was like, hey, how do we kind of encourage drivers to come to the airport, but then also make sure that there's not like a whole bunch of drivers coming to the airport, right? So we want to make sure that we balance both, city supply and airport supply. And so one of the ways we decided to do that was kind of think about this concept called ETR, which is estimated time to request. And when we interviewed drivers, the most important thing that they wanted to know is how long do I have to wait at the airport? And like we had interviewed them, we had sent them out surveys. And the biggest thing is like, I don't know when I should be going to the airport and when I should be driving in the city. And so what we decided was to build a product that would essentially let them know this by proxying wait time. Essentially saying like, hey, if you're willing to wait 15 minutes or less, come to the airport. And sometimes we might even tell you like, it's not a great time to come to the airport. You're going to have to wait over an hour to get your next trip. Some drivers are actually willing to make that sacrifice, but most drivers are not. And so a big motivation behind this product of telling drivers how long they're going to have to wait is essentially trying to, one, make sure that we help passengers who are getting picked up from the airport actually get picked up when they request an Uber. And then the second is making sure that we're not wasting drivers' time by telling them like, hey, come to the airport when there's already a ton of drivers or there's no passengers or flights landing.
Oh, that's very interesting. And I mean, I'm also kind of understanding or learning here that there is like a lot of behind the scenes work that Uber has to do with each airport to make sure there's this wait area where the drivers can actually come in and wait for their, let's say, the ride and all. Is that also a lot of work that the Uber team has to do to make sure before we even work on the technical problem, like logistically, all the airport is really well set for us?
Yeah, that's such a great comment because one of the things, like whenever we talk to airport operations, their favorite quote, and I love this quote as well, is when you've seen one airport, you've seen one airport. And that's because all airports are very different. Some airports will have waiting lots, some airports won't have waiting lots. Some airports we find that like people are actually like waiting on the street. And so like these airports are very different. The way that their demand and supply hours are all different. And so there were a lot of things we had to consider while making sure that our solution was as generalizable as possible. But we had to make sure that like when we had launched this product, we had to get, the right legal approvals. We had to talk to the airports to make sure that they knew what we were doing and work very closely with our operations partners to make sure that we launched the right product.
Yeah,
So
yeah.
this really, yeah, sorry, go ahead, Michael. Yeah.
Yeah, I think that just on top of that, I think that's also kind of like to the point like I want to make is just like the machine learning in the physical world is very different from like the machine learning on the digital world. For example, like on the digital world, for example, Facebook or like the Meta, like the Google, they are doing that search or recommendation. So everything is kind of like it's more heterogeneous and homogeneous. Basically, it's very easy to make the one solution to scale to different country or different geo regions because like the digital like features online quite standard. But when it comes to the physical world, you will encounter all kind of different problems that can't fully resolved by the automation or machine learning yet. It's still lots of things like, for example, you need to resolve by like the manually by the ops. For example, set up the geofence. For example, set up the contract, set up all the signage or the labels. Lots of things still doing today by the ops. So that's just one of the challenges. The other challenge is that the physical world is so many variable and physical laws. So it's really hard to be captured by the model itself. So we are still moving on the direction on robotics, but it's a long way to go.
Yeah, that's a great point. I actually used to work on search, and the problems in digital versus physical world are so different. One like really easy example to think about is just like curb space, right? So we can't fit like 200 drivers at one airport to just like stand at the curb, which is why we have staging lots. And that's something that you'd never have to think about when you're like on a search or recommendation platform, because in that case, like space is on.
Yeah, that's very interesting in that sense that Uber is like a mix of digital plus physical. So we have a unique set of challenges that Meta and Google seem to not have. And our modeling challenges are way complex in that sense because you have to really think about this, okay, curbside lot, okay, how many cars can really stand there, right? And that's every airport, I assume, has a very different spacing. I mean, I just experienced Delhi versus Dubai. It's like, okay, Dubai is much bigger and Delhi airport has its different terminals and all of that. I could only imagine the complexity multiplies as you incorporate all these different airports, and how do you kind of even get like a consistent set of dimensionality to really even start modeling this kind of experience, right?
Yeah. Another one point is basically that's the complexity of like doing the correct, accurate modeling. The other part is the cost of error. For example, in the recommendation system, you recommend like a wrong feed or wrong post. If people just ignore it, the cost error in the digital world is relatively small. But the cost of error in the physical world could be really huge. For example, in the rush hour, if you recommend that a driver came to the airport, then he potentially kind of waste 3 hours runtime without getting the trip. The cost of it is really huge. So that kind of like dictates how the accuracy or maybe the precision recall requirement for like the ML model in the physical world.
Yeah, and that's interesting, right? Like, yeah, what you mentioned here that we are causing changes in the physical world. And I mean, I can only assume, like, let's say, if we make a bad modeling choice, the airport might really be very unhappy with Uber experience, and they might come back to us and say, hey, what are you guys doing? You're disrupting the whole airport experience. So we are actually kind of in partnership with the city and the airport authorities in that sense. So we have much more bigger responsibility than the Meta and the Googles.
Yeah, exactly.
Yeah. So that's thank you for this kind of giving us like a understanding of the problem space. So the uniqueness, I think you guys described about like the COVID being like this trigger point, which started you guys to think about this modeling experience for airport being different than like a traditional city experience. Maybe help us understand like where did you guys start thinking about from a technical standpoint? how do you, because this is a very ambiguous problem space, I can only imagine there is so many different ways to solve this. Like either you can go operationally plus technically, or you can go completely on a technical side. Like how did you guys even start conceiving the technical land space and like moving forward with that?
Manoj, you wanna start from product side?
Yeah, let me talk a little bit about like what we kind of considered in terms of alternate approaches, and then maybe Michael, I'd love to like you can expand on like how we designed the solution to talk about our considerations. But essentially, in terms of what we considered, there were a lot of different solutions thrown out there, right? Our biggest problem was like how do we get more drivers to the airport? And one of the things that we had mentioned before was like the risk of error, right? So as we become more wrong, or we give drivers like poor recommendations, let's say, there's actually a loss of trust. And like when we interview drivers, we saw that a lot where they'll say like, "Hey, Uber sometimes doesn't always hit the mark when they tell me where to go." And so a lot of this motivation was like, okay, how do we build trust and also enable drivers to get some autonomy? Essentially, enable them to decide whether or not to go to the airport depending on information we gave them. And so when we had interviewed drivers, the biggest thing that they had always wanted to know was wait time. They want to know like, how long am I going to wait? And so really there were like a few approaches we could have taken. One was just like tell them like, hey, come to the airport and you'll get a ride, or come to the airport and like maybe you'll get a ride, who knows? The problem with that is that we were not giving them enough information or autonomy to actually like go to the airport and figure out like how long am I going to have to wait? Like what sort of ride am I getting? Like is it going to be worth it? And these are all things that are like going through their mind. The second thing that we considered was around like how much they're going to earn. So pretty much like you go to the airport, you wait for some time, and then we'll tell you like, okay, like you're probably going to earn more than if you were driving around in the city. That's actually really, really hard to model. Michael can talk a little bit more about that. But it's really hard to compare like how long they're going to have to wait, and then what sort of offer they're even going to get. Like maybe it is very likely that they're going to get a very good offer, but there's always the chance that they go there and they get a really, best way to say is like crappy offer essentially. So that imagine like you're a driver, you waited for an hour, and then you ended up getting like a $10 offer. That's not going to be very appealing to you. So what we want to do was give them an idea of like, hey, when you go to the airport, how long are you going to have to wait, and what should you expect? And so that's kind of how we landed on this idea of ETR. There were a lot of iterations that we had made to the product as we had talked to drivers as well. But I think the biggest thing that we want to make sure is one, we enable like the trust factor with drivers. So we tell them like, hey, here's information. Here's why we're telling you you should go to the airport. And then two, giving them the autonomy to figure it out themselves of, hey, if I want to wait, some drivers, like I said, are willing to wait over an hour. So at least now when they go to the airport, they know that they're going to have to wait over an hour. Whereas before they'd have no information. So when they went to the airport, they'd be like, oh, like this line is, maybe 20 cars long or 30 cars long. I don't know how long I'm going to have to wait. And that was also a big question as well, because there's a big difference between like a line of cars that's 30 cars long with, 3 flights coming in versus a line of cars that are 30 cars long with no flights coming in. In the former, you can have a 5-minute wait, and in the latter, you can have like a 2-hour wait. And so drivers would use a whole bunch of different tools like outside of Uber to figure out like when are flights landing, how many cars are in this, waiting lot, what line and what position am I in. And we just really wanted to reduce like the mental load for them and ensure that they knew when they're coming to the airport what to expect.
Nice.
Yeah, I think on the top of like the Manoj comments, I think on the engineer and the tech side, I think the way we look at the problem, I think I have like a couple of points. I think the first point is just like follow up like the cost type error. Because of cost type error, then when we do the modeling, we would make like very conscious like the trade-off. For example, like how we decide what's like our bar for the precision recall for like long, short, medium weight. So we will kind of like comprehend like what's the kind of like cost on the driver side versus what's cost on the rider side if we make the wrong decision, because there's no perfect model. Eventually, like we will try the best effort to build a model, but that with certain trade-offs. So the trade-off is really depending on like the business needs or the business evaluation about like the cost of error. I think that's the first point. The second point is basically like also the follow-up point for like the modeling on ML on the complexity in the physical world, because it's so complex. It's not really feasible to kind of like come up like very nice, well well-rounded solution in the first place. And giving like the Uber is really kind of like the moving fast company. We don't have like resources to do like a one shot to get everything correct. So you will see like we always start from simple. For example, when we first build like the, for example, some model is in the driver repositioning like the pin or like the express match. Basically, we start very simple heuristics. So basically, we just hard code some formula purely on the intuition, and we set some different parameters for different airports to start with. The next model we built for the ETR, which predicts the driver waiting time. At that time, microcontroller platform, they don't have the good support for the time series models. Model itself is not just you write something locally by the Python, everything runs. Basically, it needs to be deployed on production environment and require like platform level of the training and the inference support. So at that time, we don't have that good time series. Basically, when you need some trade-off, we just simply just choose like some built-in XGBoost, which is not the best. On the performance evaluation part, it's kind of okay. So we just like build up first version of the ML model on the microcontroller platform. Then later on, we we dive deep and deeper. For example, EPH, we get more fancy model like in the Gaussian mixture. Gaussian mixture is basically you can predict like the multiple variables, multi-head MLP. You can predict like the mean and the variance at the same time. Although like we only use like a mean to just like show the current like expected driver earning at that time, but with the variance, we kind of open the door for us in the future. We can also kind of adding the confidence like the levels for each prediction. Then later on, with like the popularity of like large language model, basically the building block is transformer. So we come to the ODS to predict like sufficiency of like, for example, density state of the drivers in the coming hours. Basically, we just leverage like the transformer architecture, which is perform much better than the traditional like the time series because it has so many kind of like the additional advantage over the traditional like the, for example, the quicker training. Basically, you can find like a correlation between like the two data points that is far away. There's so many things. I think we're just doing like step by step. I think the second point. The third point is I think also the data is first class citizen. So especially in the physical world, I think we can't get very accurate data very easily. So basically, we during our like the past like the troubleshooting or debugging, we always found that lots of times it's not a problem of the model, it's problem of the incoming data. It's basically the garbage in, garbage out. So that gave us kind of a hint. For example, if every eng team has like this 2 hours, should we keep improving model or we improve the quality of data? It ends up basically the ROI of like improving the data was really paid off rather than you just like keep increasing the models. I know many companies basically they have some of the team like maybe in a fast growing company like startup or maybe some team that really have the culture just build something just to work. They treat data as a second citizen. But I think the culture now is shifting. Now the data is being treated as a first citizen because without accurate data, we cannot really make accurate productization. We cannot rebuild an accurate model. Garbage in, garbage out, and it's caused lots of confusion and problem down the pipeline. Yeah, I think that's kind of the third point. The fourth point is kind of related to just like the forecasting the production system. I think usually we look at like we build the models, but the models not perfect. Usually we can kind of couple with feedback loops on the top of the models. So it's kind of a mixture of the reinforced learning and like the supervised learning. So we see many paradigms on like for the ODS, like the similar paradigm being made. And sorry, maybe let's pause here to say maybe.
It's interesting. I think like maybe a few points coming to my mind as you're saying. One is I think even the market has validated data is the king. Meta giving like 14 billion plus to Scale AI, and Scale AI was like data first company. They manage the data. They were like the backbone for so many large language models. So that definitely is the shift is happening, that data, people are realizing data is equally important as the modeling techniques now. It's great to see you guys also giving much importance to the data cleansing and all of that, right? And also just maybe kind of coming to my mind as you are describing this problem also, lately we had this whole travel shutdown chaos in US, right? Where the flights were all over the place. Even I heard in the news in India, some of these major airlines, they literally could not find right pilots. And for many days, the whole flights were getting cancelled. And in these cases, I would imagine our models would be at play even much more. So, as part of the modeling, before we even go into ETR, ETH a little bit more further dive deep, and Manoj was mentioning this, right? We want our drivers to really not go to other tools to really figure out, okay, how many flights are coming and do some guessing work, right? So as part of this modeling is one of the important things you guys consider around which data sources, around flight information, around rider information, how many people are coming to the airport. Does all of that also come into play?
Yeah, 100%. I feel like, as Michael said, like data was our number one thing. So even before we had built the models, we had tried to figure out like what data are drivers using and what data do we have that is available for us to actually model this scenario properly. And one example that you gave, Parth, was like flights, right? Like imagine a flight is not coming or imagine a flight is delayed. We would need to know that. And so one of the nice things was that we actually have data currently, like we have a provider called OAG, which gives us flight information. Not only does it tell us like how many flights are coming or going to land at a certain time, it also tells us like, is the flight delayed? Was the flight canceled? How many passengers are actually on the flight, or like how many seats does the flight have? And that's actually really valuable because you can also think about it from the other area where like you might have a small flight and you might have a really, really large flight. And there's a very big difference between how many drivers are going to get a request depending on which flight is landing. And drivers were already going to different products outside of the Uber ecosystem to find out like, hey, is this flight getting delayed? Is this flight landing? And so one of the things that we actually did within the card, I know we mostly have been focused on ETR, which is like the time to request, but within the UI and UX itself, we actually showed them the underlying information or the most important underlying information that we use, which is stuff like the number of flights landing and the number of cars in queue. So the moment they see ETR, they'll see like, hey, like 0 to 15-minute wait. They'll see how many cars are there. We'll say like 30 cars. And they'll also see like how many flights are landing. So we'll say like 10 flights within the next hour. There's also some really cool other data that we use, like weather data. So for example, if it's like raining or if there are huge storms, that actually might influence more people to book Uber. So you could imagine like, if there are 200 passengers coming and like they're landing from a plane, some of them might book Uber, some of them might, end up like taking some other like public transport or something. But if there's, really bad weather, maybe more people want to take Uber. So that would actually change our conversion rate. So it's not only just about like flights, but it's also about like how many people convert. And so there was a lot of thought behind what data we needed to use besides just like, hey, like let's just model this directly and see what happens. Michael, feel free to add anything that I missed.
Yeah, sure. I totally agree with like the points Manoj made. I just want to add a little bit on the engineering side. I think on the engineering type side, first thing is like there's two types of data. Basically, one is like the batch data. The other one is like the near real time or real time data. So on the engineering side, we need to handle these two types of data like differently and then carefully, especially on the real time data side. It's like need to be used for like real time inference. So lots of time inside Uber, we rely on the microlanguage team like the feature store to kind of get right like the SLA for those data. And occasionally, for example, you have to come up like fallback plan. For example, there's some like inevitable would be like data latency issues or like the wrong data issues. Basically, we need to set the bound, like say, like we don't get set some boundary. Basically, if we don't get the data right, or we know it's like we need to configure for like correct like a default value, or configure like fallbacks like a driver or rider experience. Say if we don't get the data, that will lead to the model to predict like a very wrong result. So what can we do in this time? I think that's lots of thoughts we need to put on the production, especially on the real data end. The other point is basically there's many data sources, including the weather, like for example, like the rider pulled up that's called airball data, and there are many features. Should we including everything in the model? Like what will be the importance? What is the return on investment of the features? Basically, there's some thoughts. Basically, initially we put just every feature data we thought we could be relevant into like the model performance, like the weather, like the airball or the everything. Then essentially we found like not every features are equal, especially during the model performance. So eventually that's ROI question. For example, weather data, we found it is useful, but eventually, I think 1 month to 2 months ago, we analyzed the feature importance. It ranked maybe one of the least important features. At the same time, for the pipeline that is generates the weather data, problematic because our upstream the resource is not quite stable. So we kind of make conscious decisions. Eventually, we move out this feature from this model, from like ETR. There's some decision processes, basically, like in the old days, like the PCA, like methods, similar to that stuff. Basically, everything is got ROI. The same thing applicable for the machine learning. This ROI is not just for the model performance, but also you need to consider like the efforts and time you maintain the pipeline or maintain like the online inference. Kind of another engineering trade-off there. Yeah, possibly.
Yeah, and that's really beautifully put, right? Like you're not just throwing all features that you think is important. You're also kind of being very judicious about doing feature importance, really cutting off, looking at the engineering trade-off. Because maintaining good quality data comes a lot of effort to build that pipeline, really make sure it's up to date. And also being part of Michelangelo, I know the feature store, I've worked on some of the prompts inside feature store before. It's difficult at times when you're kind of really banking on those near real-time features, and if there's some online delay or something, and you have to kind of build some alternative paths so you're not completely off from the modeling perspective, right? In terms of like your blog, you mentioned around for ETR specifically, the precision was something that improved significantly. How did you kind of choose what to really improve or optimize? Precision, recall, or other things like F1 score?
Yeah, on that end, I think there's a couple of like the big decision make to improve. There was kind of like the time like that we call the ETR code yellow. Initially, that is caused by many like the design decision and the problem. And I think that one of the biggest decision we made is basically initially we kind of use a stacked model. Basically, we model on the demand side, then we model on the supply queue on the consumption side. Then we stack those two things together. The second part is we not really use model, but more like heuristics. So we found like basically model stacking or maybe stacking a model with another heuristically will greatly amplify any errors, amplify the errors a lot. So we make big design decision to combine those two into a single model to predict the end-to-end waiting time. That really bring up like the precision and recall greatly. That's one thing to remember. The second thing is the data quality. I think back to the topic, basically like because everything is moving so fast, some team or some like maybe the project like we try to kind of deprioritize like the data, and we at that time we really serious like to check every data set to check any anomaly or record. We ask it to different teams to get like upstream, downstream the data fixed. Yeah, here is point. Basically, data is not only by particular team, for example, airport team or travel team. Usually, many data derived from many other metadata or like data from different dependency teams. Fixing data is not really trivial. So last time you need to like collaborate cross-functional to escalate on different teams to work together to get the root cause fixed. Another thing is like also on the data is not just correct or wrong or correct. Basically, for every team or dependency, they have their own assumption of the correct data, which may or may align with your definition of the correct data. So last time it's not just for engineering work. Last time, for example, Manoj product or do lots of the communication to make sure everyone really align with the like the metric definition, which makes sense, which doesn't make sense, which is nuanced. So it's hard. So there are many other smaller things we do, for example, to fix model. Basically, I think we adjust maybe the kind of like bar for like precision and recall for each like the short, long, and high based on the business importance. That's also the third one. Beyond that, there's a couple of smaller things we make together to make fix the model. Yeah, Manoj, like let me know if I missed anything or close work on that model code as well.
The code yellow stuff was interesting. So just for context, like kind of what happened was we kind of, yeah, like as Michael said, we built two different models and we found that the error was compounding. And then there were some airports where like, hey, the wait time that you're showing versus the wait time that's actually there is very different. And so one of the things that we had to do was actually remove the reliance on building that, remove the reliance on building a stack model. But I think from the product side, what was interesting was that rather than thinking about from the modeling side, I had to work with a lot of stakeholders to figure out like what is acceptable. Like, is it okay if sometimes like maybe we don't show ETR, or like at what point do we deploy this model? And so what we had chatted about it. One of the fun things is always explaining machine learning, like precision recall F1 to people who are not super familiar with it. And you have to break down the concepts and say like, oh yeah, precision is like how often you're right, recall is like how often you make a prediction, um, and then talking about like coverage and stuff like that. One of the things we ended up landing on was like, hey, in order for us to re-release our model, so we actually rolled it back for Code Yellow. In order for us to re-release our model, they're like, okay, like if you're able to do a precision of 80%, for these airports, like you can release it. And some airports had, as we had talked about, airports are all different. So some airports were a little more okay with having a more lenient threshold, and some airports wanted to be very strict, and that was just dependent on their driver base, because like some drivers really wanted accurate information, some drivers didn't, and it also, as Michael said, like might have also depended on the data, because like some airports have a lot of activity at Uber and some airports don't, and so the more sparse the data is, the harder it is to actually like build an accurate signal.
And do you have to collect like feedback from either the ground operation team or the driver itself to really kind of make that call? Because it's a difficult call, right? Like how do you make per airport like call, okay, what to really optimize here, right?
Yeah, it's not easy. We do both. So we got feedback from the drivers. We got feedback about the product around like UI UX, and also like the thresholds and like even the ranges. The three buckets for ETR: 0 to 15 minutes, 15 to 30 minutes, and then over 30 minutes. And the ranges were both informed by like the technical limitations of like, maybe if we could do 10-minute increments, that would have been better, 10-minute increments to an hour. But then like the further out you go, the harder it is. So if you did 0 to 10 minutes might be very easy, but then 50 to 60 minutes might be very hard, right? And so that's kind of why we had to like make the buckets that we did. So we had to get feedback from the drivers, and then we also had to talk to the operations team to say like, hey, like here's what we're building, here are the thresholds that we're having, here's our data, and then they also gave us the check mark. They would even work with the airports to figure out like what do we show. So it's a very, very collaborative product. It's not as easy as like, let's build a model and launch it. It's really like, let's build a model, let's get feedback from drivers, airport ops, and then the airports themselves, and then let's figure out how do we launch this together.
It's really a whole cycle, looks like, yeah.
Yes, yeah. There's like the ML model development cycle, and maybe like the the collaboration cycle as well.
Yeah, exactly. It's really beyond the engine, like product ops, like the other stakeholders, like customers, the riders, drivers, like all feedback within. Yeah. Another point I just I forgot to mention, basically, it's also on the data side. Basically, the availability of data for each smaller airport also have impact on how we do the modeling. For example, should we do like the global model, or should we do the partition model? So for example, for the ETL or EPH, basically a lot of smaller airports have very sparse data. Make it like doing the partition model is really hard. So essentially we build the global model first. Then we will try to test on when we launch it, we will just keep very close eye on like how that model performance on the smaller airport to see if any customization on characteristically is needed for each smaller airport. So it's more like code start, and it's not code start, exact code start basically. It's more like that sparsity on the data depends on which you have like global model, partition model.
So a lot of the design decisions is not just, oh, hey, I'm just building a model. This actually, you're also going nuance by nuance into airport availability of the data and really making those trade-offs. So different airports might have partition model versus like, okay, some airports might just be good with global model given lack of data maybe.
Yep, exactly. Yep.
And on the modeling side, it's also something caught my attention in the blog, which is around this the transformer style architecture, which is inspired probably by like the recent improvements, right? So I see like a whole lot of layers of this encoder into the architecture. Like maybe if you can give us some insight into what inspired kind of that level of complexity in the model architecture.
Yeah, sure. I think the transformer is like the recent emergent model. Basically, it has many advantages to the traditional model, for example, LSTM. The reason I think this came to about maybe like 3 or 4 bullet points. The first one is like the transformer architecture is really good for the parallelization. So, for example, for the traditional LSTM, for each process, you need to wait like all the previous steps. It's basically more like sequential, like based on the timestamp. But the latest transformer model enable us to do the parallel training, so which greatly improve the speed. So it's not only applicable for the large language model, like for example today's ChatGPT is based on that architecture, but it's also can help on the forecasting. So that's one reason we use it. Basically, you saw all the other, like maybe the foundation forecasting model also use that paradigm. The second thing is basically for the transformer, it's able to capture the long range dependencies. For the LSTM, basically you only depend on like last few steps, like dependencies. You can't, the dependency tree cannot be really back traced very long like the before. So this thing is also benefit from like a parallelization. Basically, because of the efficiency of parallelization, you can capture this long range dependency. For example, the Thanksgiving today, the traffic of demand of the Thanksgiving today could depend on the traffic on the Thanksgiving last year, which is really long window. This kind of like dependency is really hard to capture by traditional LSTM or like a deep learning or non-deep learning time series model. The third thing is like the dynamic weighting. The dynamic weighting, for example, the dependency of like the last Monday versus dependency of current, like the request of last close to the holiday, definitely has different like the weights. So transformer is really good at like capture the dynamic weight, just like how it did in the large language model side. The fourth thing is because of the capability of computation, it's really easy for transformer to handle multivariate data. So basically, if you have many variables in the time series, how they correlate the same prediction target is much easier. But also it boils down to the data side. I believe only if like the data is really it's really huge, so the transformer can outperform. If the data point is not that much, so I believe it's not that better than the traditional models. Yeah, that's my take on why we adopt transformer. I think that's also prepared for the future. Even today, we don't have enough data sets to kind of like justify the needs. But in the future, I think as long as we accumulate more and more data, basically the transformer will be outperform others. Basically, I chat with other people on different areas, especially in the digital world. Like for example, today they do the home feeds recommendation or like the personalization. I think the transformer architecture become like the default building block for all those use cases as well. They no longer use very traditional like a two-tower stuff. It's kind of very old school.
Yeah, it's interesting. I think I'm really realizing from all the stuff you described that as a modeler, you just can't go with every new technique out there and just think like this will just work for my use case. Requires a lot of thought and judiciousness, judgment about like what is the right architecture that will fit my use case, right? And otherwise you might end up doing something cool that you think is cool, but it really doesn't serve your use case, right?
Yeah, exactly. It's kind of balance. Basically, the latest thing doesn't mean it's good, but if we always be very conservative, only look at ROI, not try to take any risk, that's another problem. So it's kind of a balance. Basically, as a company, we definitely need to look at the ROI in the short term, but it's also good to allocate certain percent of energy, like engineer or like the product resource on some new bet. It's a trade-off.
Yeah, nice. Yeah, and I am like after all this whole wonderful set of improvements, did you guys like get direct user feedback or user experience, or I mean like what was that thing that helped you like really land that, hey, we really made good solid improvements now and the product is much better? Like how did that conclusion come about?
Yeah, so we actually got feedback when we had launched the product. We actually got feedback from drivers. I think initially they were just very excited about the product, like, and I'm talking about like V1, like before we had made changes in the model. I think they were just excited that like we were giving them information. I remember like even my ops counterpart had said he's on like some Facebook groups for his particular airport, and he forwarded me people saying like, hey, like Uber launched this. Did you guys see this? It's actually really cool. And so we had taken this qualitative data, and then when we had relaunched the model as well, we had also seen like, okay, on these Facebook groups, like, has the opinion changed around, the accuracy of what we're showing. I will say there was a data sparsity problem. It's not only just in modeling, but it can also be with customer feedback, where generally, like, unless you've really knocked it out of the park or you've like really wronged your customer, most customers don't give a lot of feedback. So we had to scour through a lot of different socials, so like Facebook, Reddit, direct driver surveys, asking. We actually asked our operations folks to like talk to drivers on the ground, see whether they're using this product and see whether it's helpful or not. And what we had found was that like after the changes we had made, especially for the Code Yellow stuff, it actually improved the driver's experience. Obviously, we ran an XP and AB and everything like that, at least for the first version, and we saw like very positive business results. I think that might have been outlined in the blog, but in terms of like customer perspective, we also found that it matched the business results, and I think that's where I was really excited to see that like drivers really loved the product, and it was something that like if a driver had never used it, they would have never said that it was inaccurate. A lot of the Code Yellow was actually inspired by drivers telling us that the wait time of what they saw versus what they were experiencing were different, and that really encouraged us to build a better model.
Yeah, yeah. I think just on top of that, it's just like we did due diligence to really kind of like, for example, we shut down the product for some cities for a time once we detect like the kind of like the discrepancy is above certain threshold. And in the production, it's really impossible to like forecast like the 100%. I think there's some threshold we set to make sure that even in the worst case, I think the driver still has a good experience with Uber. So we keep the like guardrail really tight.
Yeah, I actually think one of the fun things, actually, Michael, when you said that we shut it down, one of the things that I remember is when we had shut down the product, even though it was inaccurate for some airports that we shut it down at, what we found is that drivers were actually clicking that surface a lot more and like scrolling around, looking for the product that we had shut down because they were used to it, they were using it. And now they're like, where did it go? And so we had turned it on as quickly as possible. But I think that's some validation of like, even if the product's not perfect, even if the model is not, like 100% accurate or maybe even 90% accurate, as long as it shows some sort of validation for the user, so it gives them like information that they otherwise wouldn't have, they're pretty happy with it. And so like obviously there's a big difference between like never being right or like only being right 50% of the time, like flip of a coin, versus being right like 80 or 90% of the time. But I think like just the idea of like us removing the product and like drivers actually like scrolling through to look for it again showed that like we were on the right track and we just needed to improve the model and improve the data, the underlying data to build a better user experience.
Yeah,
This is fantastic. Getting early signals, it validates you, motivates us as engineers that hey, you really are on the right track to solve the right problem at least.
Right.
I mean, I've loved all the experiences, all the technical insights you guys have shared today. Any other things you would like to kind of like close off with from what you guys have done? Wonderful work here. Yeah.
Just one more thing, like the big thanks and kudos for the micro-launcher platform team. Basically, without the micro-launcher platform team, to productionize any model is really, really hard. So there's so many like problems. The product team cannot really handle it by themselves. I think it's really, really, really appreciate the help. We get really great support from like the platform team. Now I think so many things is happening on the micro-launcher platform, agentic AI, or everything is. I'm really excited. Maybe in the future we can do some kind of similar integration to build a very innovative product at airports to leverage the latest like the generative AI agency.
Yeah, like just like piggybacking off Michael's point, Michael and I are here to represent the work that was done by the team today, but there were so many people involved. Like I said, like airport ops, different product teams, the Uber AI team, both Michelangelo and product. So like Bob, who couldn't make it today, but was a very pivotal part of the modeling part. Like it's definitely like a product built by a tribe, and I think that's something that I really appreciate at Uber is like people are very happy to work with you and very collaborative, and it was probably one of my favorite products I built while I was on the airport team.
Yeah. Echo on that. Just like Uber AI, basically we plug into the airport team to make that happen. Like the Bob, June, Winnie, and many other folks. Yeah, it really they contribute the code. I think it's really very close collaboration between like the Uber AI and the airport. I think the airport team did initial like ETR 1.0 by ourselves, but we feel like we are not really kind of like really kind of like that. We don't have like that organic MLE from the team. Basically, a lot of like resources from the Uber AI, and then we build a product together on the top of microcontroller platform. It's kind of really win-win-win for the the teams, like the product team, like the Uber AI team as the ML domain expert, and the microcontroller team as a platform team. So it's very seamless, like the collaboration.
Yeah, and it's lovely to see that. I think like I've almost finished 5 years now, and I felt like this company in itself is very of a collaborative nature rather than me versus you kind of thing here. So, and people like to really collaborate, do more, and I think that one Uber spirit is something what you guys are saying. It looks like that came across very strongly in that the whole problem that this was solved around. Yeah, fantastic. Thank you, Michael. Thank you, Manoj, for being on the podcast, and it's lovely to see the great work you have done, and hoping that we can collaborate more on the Michelangelo side also in future.